In this synoptic chemistry video, we're going to look at the ozone layer and the effect of CFCs. So what is ozone? It's an unusual molecule with the formula O3. So it contains 3 oxygen atoms bonded together. The bonding is similar to benzene, if you've covered that so far. So it contains these things called resonance structures. It's alternating between the double and the single bonds and moving around between the molecule, and you end up with a delocalized pair of electrons across all 3 oxygen atoms. So each of those bonds is basically the equivalent of 1.5 bonds as opposed to being an actual single or double bond. Ozone is a very nasty chemical. It's a respiratory irritant. It sometimes forms at ground level in what we call the troposphere during lightning storms or in photochemical smog, so it can be a result of other chemical reactions. Higher up though, in the stratosphere, we have what is called the ozone layer, a layer of ozone. And this is formed because of the absorption of UV light up in the stratosphere. So oxygen diffuses up towards the outer parts of the atmosphere, where they are exposed to a much higher intensity of UV light than they would be down here at ground level. So on absorbing that UV light, some of those oxygen molecules are going to break up, a process known as homolytic fission, which you should have covered in your free radical reactions. So this forms 2 oxygen radicals. When an oxygen radical, so that's happening when it absorbs a particular frequency of UV light because of the particular strength of the oxygen-oxygen bond. Oxygen radicals are extremely reactive, and so the oxygen radical is most likely to hit an oxygen molecule, and when it does that, it's going to form ozone. This reaction is making a bond when the oxygen radical reacts with oxygen, so it's actually exothermic. It releases heat and leads to a warming of the upper layers of the stratosphere. So actually, the higher up in the stratosphere you go, the hotter it is, which is kind of the opposite to what you expect down here in the troposphere, where it gets colder the higher up you go. So why is the ozone layer important? As we've just said, ozone absorbs UV light itself, not just oxygen. And it just so happens that the particular wavelength, the frequency of UV radiation that is absorbed by the O3 molecule, which of course has different bonds to the O2 molecule, that is the particular frequency of UV radiation that is most harmful to life on Earth. So the ozone molecule absorbs UV light, just like oxygen is then going to break down. Is going to break down back into the O2 molecule and the oxygen radical. So you may sort of seem like, well, what's the point of that? You know, the oxygen absorbs light, turns into oxygen radicals. Oxygen radical forms ozone, and then ozone just absorbs the light and goes back to forming the oxygen radical and the oxygen again. But what's really important is the frequency of that UV light that's absorbed only by ozone, because all of the frequency of light absorbed depends on the particular strength of the bond being broken. And that is our most harmful frequency. Without the ozone layer, in fact, many scientists think that complex life would not have been able to evolve outside of the oceans, because UV exposure leads to DNA damage and cancer. And for millions of years, the overall concentration of ozone in the ozone layer has remained roughly constant, because there was an equilibrium established where the rate of ozone formation is equal to the rate of ozone destruction by that absorption of UV light. So now let's move on to these things called CFCs. CFCs are a group of compounds. Their full name is chlorofluorocarbons. So they're basically alkanes where all the hydrogen atoms have been replaced by chlorine and fluorine atoms in varying different quantities. You've got a couple that you can see here. Their systematic names are a bit of a mouthful. So we would have trichlorofluoromethane, or we'd have dichloro-difluoromethane, and so they tend to just be given codes like CFC11. So CFCs are extremely unreactive. That's because of the strength of the carbon halogen bonds. So those bonds do not break easily. They're also volatile, so they are gases, but they can be compressed to form liquids, and they are non-toxic, and they are also non-flammable. So what were they used for? Why were they developed? CFCs were invented by a scientist called Thomas Midgley in the 1930s. Now, Thomas Midgley is actually known as potentially the most dangerous man who's ever lived, one of the most harmful inventors in history. And that is because before he even came up with CFCs, Midgley was also responsible for the introduction of lead additives to petrol to improve engine efficiency. I'm not going to go through his whole life in this video, but I do recommend you search him up, find out more about his story, because it's really interesting and quite sad. Okay, so we put lead additives in petrol, and then to make up for that slight wrongdoing in terms of atmospheric chemistry, he decided to look at refrigerant gases. So in the 1920s, household refrigerators were getting very popular, but they had very dangerous compounds that they used for the compressed gases that make the refrigerator work. So, for example, they could have something called methyl formate, which was toxic, and sulfur dioxide, toxic, irritant, corrosive. So Midgley led a team of scientists to come up with an alternative compound, dichloro-difluoromethane, which he just marketed as Freon. He was so proud of this extremely safe, non-flammable, non-toxic gas that he actually demonstrated that by taking a big lungful of the gas and then using it to blow out a candle to show that they were completely safe and non-flammable. And because of this, CFCs became hugely popular in a very short length of time. They weren't just used in refrigerators, they were also used as solvents, and they were used very much in aerosol propellants. So what is the problem that CFCs caused? It wasn't discovered until decades after their use became so widespread. And the problem is because the CFCs are so unreactive. So most compounds will break up and react with other substances down here in the troposphere, in the lower layer of the atmospheres. So most of the stuff that we make or generate, most of the chemicals and the pollution that we create here on Earth doesn't get up to the higher reaches of the atmosphere. But because CFCs are so unreactive and inert, they will diffuse and eventually travel up to the stratosphere, to the ozone layer. And here is where there is a higher intensity of UV light, which means that chemical reactions can start to happen. So this UV light can be absorbed by the CFC molecule, and it's going to break this carbon-chlorine bond to form a chlorine radical, and the other part of the molecule will also be a radical species. It's always going to break the carbon-chlorine bond. The carbon-fluorine bond is too strong to be broken by those frequencies of UV light. So we've created chlorine radicals. We've finally kind of got this molecule to react. And you may remember from the reaction between chlorine and alkanes, chlorine radicals are very reactive species, and all they will do is whatever they collide with, they will just kind of take an atom of that molecule. So it's in the ozone layer, the most likely thing that the chlorine radical will collide with is an ozone molecule. When it does that, it's going to remove one of the oxygen atoms. It's going to leave behind molecular oxygen, O2, break up the ozone molecule, and it's going to make a ClO, which is also a radical. So what we've done here is we've broken down ozone. Now ozone is always being broken down, but normally ozone is being broken down in the process of absorbing harmful UV radiation. So the chlorine radical is breaking the ozone down without it doing that absorption process. We're then leaving behind this ClO. That's got an odd number of electrons too, so it's also a radical. And if a ClO radical reacts with an oxygen radical, remember there are oxygen radicals around because ozone breaks down into O2 and O when it absorbs UV, and oxygen itself breaks down to form oxygen radicals when it absorbs UV. So there are a fair number of oxygen radicals around. The ClO radical will react with that to form an oxygen molecule and a chlorine radical. So the chlorine radical has been reformed. And what we've done there is remove the oxygen radical. Now the oxygen radical was important, if you remember, because the oxygen radical is how ozone is made in the first place. It's when oxygen radical combines with O2 that we get O3. So there are two ways that ozone is being depleted, one by directly reacting with ozone, and the other is by removing the oxygen radical so we can't make any more ozone. We said that the chlorine radical has been reproduced. So if we combine these two equations, the net effect is that a molecule of ozone is reacting with an oxygen radical to make O2. And during that process, the only UV light that is absorbed is that little bit of UV light at the start to break the carbon-chlorine bond. That's not the same strength as the ozone bond, so it's not the right frequency of UV to be offering the maximum protection to life anyway. But also the other problem is that the chlorine radical has been regenerated. It's not being used up in the process. It's not in the overall reaction. It gets used up and then remade. The ClO gets made and then used up. So that means we've estimated that a single chlorine radical can take part in this process about 10,000 times before it leaves the stratosphere or reacts with something to take it out of this process. So even though the use of CFCs has been banned for many decades, the damage to the ozone layer is taking a really, really long time to repair because it was so significant, because catalysts can just keep going. So we've banned, internationally, CFCs have been banned since 1987, so really long time. And as alternatives, we use compounds that contain at least one hydrogen atom. They're very similar, so they may be called HCFCs or HFCs. We've got a bond there which is weaker, and that allows these molecules to break down in the lower layers of the atmosphere before they can get up to the stratosphere. So they don't do anywhere near as much damage to the ozone. However, they are not without their problems, and that is because these molecules are sadly very potent greenhouse gases, because carbon halogen bonds are very good absorbers, and CH bonds, as we know from methane, are very good absorbers of infrared radiation. And so in fact, in terms of their use in propellants, in terms of spray cans and things, they have been banned also since the 90s, but they may be used elsewhere. Finally, CFCs are not the only compounds that cause damage to the ozone layer. We've got another problem that nobody's banning, and that is nitrogen oxides. So nitrogen monoxide is actually, although we often just write it as NO, it's actually a radical, because if you think about it, nitrogen has 5 in its outer shell, oxygen has 6, so we've got an odd number of electrons in that molecule. So NO or NO2, so nitrous oxides generally, they're formed wherever the temperatures and pressures are high enough for nitrogen and oxygen from the air to react with each other. So this includes car engines, lightning bolts, and jet engines. So if it's formed close to the ground from a car exhaust, it's a very nasty pollutant. It causes respiratory issues, it causes photochemical smog and acid rain. but it doesn't stay in the atmosphere that long because it dissolves into the rain. But higher up in the atmosphere where planes go, the production of NO in jet engines is a real problem. So we've said that NO is a radical, and therefore it is going to basically do exactly the same as what the chlorine radical is doing. So if we look at the first reaction, it combines with O3, it takes off an oxygen and leaves the O2 behind. It makes NO2, a little bit of adding up. I've got odd number of electrons on my nitrogen, even on my oxygens, so that is still a radical species, NO2, although we often do write it in chemical equations, we don't actually sort of say that, but it is a radical, it's very reactive. And then that can then further react with oxygen radicals exactly like the ClO radical did, gives the oxygen back to make O2, and you can see that the same overall process is happening. O3 reacting with oxygen radical to make 2 molecules of O2.